Hi everyone, this is IIRusingButterworth1. In this video, I want to explain how to design a low-pass Butterworth filter with the given specifications. So to design IIR filter using Butterworth analysis, we have to follow particular procedure. Right? So I will explain that procedure stepwise with one example. Design a low-pass Butterworth filter, with the given specifications. So these are the given specifications. Alpha P is 3 dB, 3 decibels at cutoff frequency 1.5 kilohertz. And similarly, one more parameter also there, that is alpha S. Alpha S is 40 decibels. Alpha S is 40 decibels at cutoff frequency 3 kilohertz. So now we can consider these frequencies as passband frequencies and stopband frequency, because here alpha P is given. Alpha P is a attenuation factor according to the given specification. Alpha P is attenuation factor for passband, right? This is defined for passband and this is defined for stopband. Attenuation factor for passband and stopband is given. These values are always available in decibels. And this passband attenuation occurs at one frequency. The frequency is 1.5 kilohertz. So we can take this as a passband frequency, and alpha S is 40 decibels. So now we can assume this as a stopband frequency. So passband frequency is there, stopband frequency also given, and attenuation factor for passband and attenuation factor for stopband. From these given parameters, first of all, we have to find angular frequencies. Angular frequencies, that is passband frequency and stopband frequency. That is like this: omega p. Alpha p is a 2 pi ft. So angular frequency in terms of frequency, so the standard formula is 2 pi ft. Then substitute here passband frequency 1.5 kilohertz. Then we will get here 3000 by radians per second. And similarly, now I want to find stopband. Now I want to find stopband angular frequency. That formula is 2 pi fs. So substitute here fs 3 kilohertz, then which gives the 6000. Here let us take 3000, and this one is 6000 by radians per second. So to find or to design a low pass Butterworth filter, first of all we have to find angular frequencies, passband angular frequency and stopband angular frequency, and similarly we have to find another two parameters. Those are lambda and epsilon. Lambda is also called as attenuation parameter or stopband parameter. This is equal to 10 to the power of 0.1 alpha S minus 1. This is one of the standard formula derived from the Butterworth filter analysis. And similarly, epsilon is a passband parameter. This is equal to square root of 10 to the power of 0.1 alpha p minus 1. So first of all we have to find these angular frequencies and these values, right? And later find the order of the filter. This is comes under second step. So I will write as a step as per procedure. So determine angular frequencies and lambda and epsilon. These are comes under first step, and in second step we have to find the order of the filter. From the Butterworth filters, the order of the filter standard formula is defined like this: n is greater than or equal to log means here base 10. So log of lambda by epsilon by log of base 10 omega s by omega p. Log of omega s by omega p, stopband frequency and passband frequency, lambda and epsilon. See, try to substitute this alpha s and alpha p in this lambda and epsilon equations, and omega s and omega p in this order equation. then we will get the value approximately I am taking here. So already I have calculated these values, so approximately this gives the 6.647. So n is the integer value. This order of the filter should be integer value. Always we have to take greater than or equal to this value. So now I'm taking in terms of integer, this value is approximately equal to 7, right? So according to the given specifications, the order of the filter is 7 here. So this is comes under second step. We have to calculate the order of the filter, and later we have to find the poles, right? So those poles comes under the poles calculation comes under the third step. So poles location, now I'm writing one standard formula like this: Pk is equal to omega c e to the power of j pi k. This is one of the standard formula for finding poles. Omega c is a cutoff frequency. Omega c is a cutoff frequency. For easy calculation purpose, I am assuming here omega c is equal to 1. Otherwise, we have one standard formula also there to determine omega c. Omega c is equal to omega p, passband frequency, by epsilon whole power 1 by n. This is one of the standard formula here to determine cutoff frequency from the passband frequency, and if you want, you can find from the stop band frequency, right? If you want find from the stop band frequency, then the equation becomes omega s by lambda power n. So lambda is a stop band parameter and epsilon is a passband parameter. Here I have wrote omega p, passband frequency, that's why here I am using epsilon parameter. So if you want to find cutoff frequency, exact cutoff frequency, use this formula, substitute the given values, then you will get the cutoff frequency here. For easy calculation purpose, here I am assuming omega c is equal to 1 radians per second, right? This is assumption case, but if you want to find exact analysis, compulsory we have to find their cutoff frequency. Now use this formula, then find out the poles. First of all, I want to find the angle here, pi k is there. To find pi k, another standard formula is used from the Butterworth filters, that is 5 by 2 plus 2k minus 1, 2k minus 1 into pi by 2 into n. Here the k value starts from 1 and defined up to n. Here I have wrote the formula is 2k minus 1. Sometimes we can use 2k plus 1. But if you write here 2k plus 1 formula, there the k range will changes here. K range starts from 0. So if the formula consists 2k plus 1, then the k range starts from 0 onwards, 0 to up to n minus 1. Now here I have wrote the formula is 2k minus 1. That's why the k value I am stating from 1 onwards up to n. So n is the order of the filter. Now here 7 is there, so finally we have to find this value 7. 1, 2, 3, 4, 5, 6 up to 7 here. Right? So we have to substitute these values in this equation. Then finally we have to write all the angles. First of all, I am writing one angle here. K is 1, then pi by 2 plus 2 minus 1 is 1, so then it becomes pi by 2 into n. N is 7 is there, so then finally which becomes here 14. So 5 by 2 plus 5 by 14. Then the value becomes here 4 pi by 7. So here I have wrote 5 1 and similarly find 5 2, 5 3, 5 4, 5 5, 5 6, 5 7 up to 5 7. So now I am writing those values directly here. Phi 2 is pi 5 by 7. Just we have to substitute in this, k is equal to 2, and pi 3 is 6 5 by 7, and phi 4 is 5, and so totally 7 angles are there, 1 to 7. So phi 1, phi 2, phi 3, phi 4, phi 6, phi 7, phi 7, phi 6 and phi 7. these 7 angles substitute in this poles location equation. From that directly I am writing now P1. P1 explains the e to the power of j 4 5 by 7. 4 5 by 7. So just try to find the value of this using another standard formula, e to the power of j theta formula, this one. E to the power of j theta is equal to cos theta plus j sin theta. Right, cos theta is the real term and sin theta is the imaginary term. Use 4 5 by 7 plus j sine of 4 5 by 7. So here I am writing the standard procedure for one pole, and similarly you have to find the remaining poles because here 7 times we have to apply this formula. And if the angle is 4 by 7, then the simplified answer should be like this: cos 4 by 7 is minus 0.2, approximate value I am writing now. And if you have calculators, try to calculate all these values, right? So approximate value should be minus 0.2 plus 0.97. 0.97. So this, if the angle is 4 5 by 7, then the resultant value is this value. Similarly, you have to calculate remaining poles P2, P3, P4, P5, P6 and P7. Just you have to substitute this angle in this equation. So here one standard formula is defined here. Just substitute all these angles in this equation, then you will get the poles values. So now I am writing those values directly. Right, P2 is minus 0.62. I am writing all these are approximate values. Right. So already I have calculated these values. That's why I am directly writing these values, approximate values. If you want, use calculators and determine all these values. So P3 is minus 0.9 plus j 0.43, and P4 is e to the power of minus j5, e to the power of plus j5. E to the power of plus j5 is cos 5 minus j5, that becomes minus 1, and P5 value we will get here minus 0.9 minus j 0.43. And once again I am saying here these are approximate values. That P6 is minus 0.62 minus j 0.78, and P7 is minus 0.22 minus j 0.97. So these are the poles. If you want to locate these poles on S-plane, just try to draw one S-plane here. S-plane consists of one imaginary axis and real axis, right? So try to observe all the poles values consists real parameter and imaginary parameter, but the real parameter is here negative, right? And sometimes the real parameter we will get here positive values, but don't consider those poles, because for stability analysis we have to consider left side poles only. If the poles of the system are located left side of the S-plane, then the system is stable. So that's why here we will get the values exactly negative real values. Imaginary value is either negative or positive. Don't bother about that one, because this axis is positive imaginary axis and this axis is a negative imaginary axis and this is negative real axis, right? So if you locate all the values here, all these poles, suppose I am taking P1 pole minus 0.2 j 0.7, so let us assume this is here, right? And exactly one more angle, one more value also there, that is right, P1 and this one P7 is minus 0.2 minus j 0.97. Real value is negative, but imaginary value is here negative, so you have to locate here. This is, I am assuming, minus 0.97 and this value is 0.97, right? If you locate, if you find the location of the remaining poles, those are located like this. right? Totally 7 poles are there. And if you combine all these lines, just acts as one semicircle, because Butterworth filter analysis explains all the poles are located on this circle. The circle radius is here, unity radius, because here I have assumed omega c value is how much? 1. If the omega c value is some other value, then the radius of the circle also changes. And similarly, we will get the poles location towards the right side, but we are not taking the right side poles for stability analysis. We have to consider always left side poles only, right? So after finding the poles, finally we have to write the transfer function equation h of s. From the Butterworth analysis, the h of s transfer function, linear transfer function standard formula explains omega c by s minus s1 s minus p1. So here I am assuming poles locations are p1 like this, right? S minus p2 and s minus p3 up to order of the filter. So finally you have to write s minus pn. Now in the above system, in this system, the n value is 7. So finally we have to write here 7 poles, right? So already we have assumed omega c is 1 radians per second. Then final analog transfer function is 1 by, because here I have assumed omega c is 1, s minus p1. So p1 pole is a minus 0.2 plus 0.97. So if you write this one, then it becomes 0.2 minus 0.97, right? And similarly one more pole also there, p7. p7 is minus 0.2 minus 0.2 minus 0.97. so here we can write directly plus or minus j. Okay, directly I am writing the 2 poles at the same point here, right? If you want, you can write separately. Okay, so similarly the remaining poles location, s plus 0.62, right? And finally one more only real value is there, that is s plus 1, right? So here 1 pole and here 2 poles, and in this 2 poles, okay, so here 2 poles. Finally the number of poles are 7 poles. So now finally I have wrote final transfer function using 7 poles according to the given specification. This is the transfer function using Butterworth analysis, and this is considered low pass filter Butterworth, low pass Butterworth filter, and this is a standard procedure. So try to follow these steps. First of all, we have to determine these frequencies: passband frequency, stopband frequency, and lambda and epsilon, these parameters. And later try to find the order of the filter using this standard formula, order of the filter. And the third step explains the find the poles location. Before this you have to find one more value, that value is cutoff frequency omega c, right? That is omega p by epsilon power 1 by n, and otherwise we can assume omega c as a 1 radians per second for easy calculation purpose. So use this formula, phi k, angle pi k is equal to pi by 2 plus 2k minus 1 into pi by 2 into n, and in this you have to substitute k values 1, 2, 3 up to n value. N is the order of the filter. So substitute those values and find out the angles and poles. Then finally write a analog transfer function. So this is the standard procedure to define the analog transfer function using Butterworth. And later we have to convert this analog transfer function into digital transfer function using transformation techniques. Those transformation techniques are impulse invariant method, bilinear transformation method, right? Approximation of derivative method. Different methods are there, and most widely used methods are impulse invariant method, bilinear transformation method. In this video, just I have explained how to define the analog transfer function from the given specifications. And in next videos, I will explain the complete design of the digital filter using Butterworth impulse invariance method, Butterworth bilinear transformation method. This is comes under analog transfer function using Butterworth